everyone. Welcome to this session on frequency response analysis in control systems. In this video, we will explore what frequency response is, why it is important, and how it helps engineers design stable and efficient systems. So, this concept is widely used in power systems, communication, and motor control applications. Why frequency response matters? So let's begin with the real world problem. In many engineering systems, we often struggle to predict how a system behaves when inputs vary in frequency. For example, in power systems or communication systems, signals operate at different frequencies. So if we cannot predict system behavior, it may lead to instability, poor performance, or even equipment damage. This is where frequency response becomes essential. It allows us to understand system performance across a range of frequencies. So next one, the limitations of time domain analysis. Traditionally, we analyze systems in time domain. However, this approach has several limitations. First, it is difficult to predict steady-state behavior using time domain analysis. Second, it becomes very complex for higher order systems. And most importantly, it does not provide direct insight into how the system behaves different frequencies. So, while time domain analysis is useful for transient response, it is not sufficient for complete system understanding. So now let's see the time versus frequency domain analysis. So let's compare both approaches. In the time domain, analysis is complex for higher order systems, no clear frequency insight, and steady-state behavior is not easily visible. In contrast, the frequency domain analysis, it simplifies analysis and clearly shows system behavior at different frequencies and provides direct information about steady-state response. So this makes frequency domain analysis as a powerful tool for engineers. Now let's define the frequency response. So frequency response is the steady-state response of a system when the input is sinusoidal input. If in the mathematical representation input r of t is equal to r into sine omega of t, then the output will be also sinusoidal. C of t is equal to c into sine omega t plus phi. Here the c represents the amplitude of the output and phi represents the phase shift. So this means the system changes both the amplitude and phase of the input signal. So understanding frequency response, the input is sinusoidal input and also we got the output as sinusoidal one. So here the x-axis represents the frequency and the y-axis represents the amplitude of the particular signal. So in blue color it represents the input signal and the red color represents the steady state output of the signal. So from that the 0 to pi it represents the time period t and the phase shift angle g of j omega is equal to 2 pi del t by t. And we can calculate the amplitude ratio using the formula modulus of g of j omega is equal to mod of y of t divided by mod of u of t. Now let's understand the mathematical representation of the frequency domain representation. In this frequency domain, we can represent the s is equal to j omega. So we can calculate the transfer function in complex representation. So t of j omega is equal to t modulus of t of j omega angle of t of j omega. So here the mod of t of j omega represents the amplitude changes and the angle represents the phase shift. So thus the output magnitude is equal to input into modulus of j omega. Output phase is equal to input phase plus system phase. And this represents the frequency domain block diagram of the particular signals. And the key frequency domain specifications. The first one, the resonant peak. The resonant peak, it represents the MR. This is the maximum value of the system as magnitude response. Second, the resonant frequency omega R, the frequency at which this peak occurs. The third one is the bandwidth omega B, the range of frequencies where the system performs effectively, typically up to 70.7% of the magnitude maximum response. So these parameters help us to evaluate the system performance and stability. Next we go for the practical applications of frequency response. So it has a wide applications in control systems and etc. First one is the power system. So it helps in analyzing frequency stability. In communication systems, it is used in filter design and signal processing. In motor control system, it helps in controlling speed and position effectively. Now let's move on to the summarization part of this video. To summarize this, frequency response helps us understand how systems behavior under different frequencies. So it overcomes the limitations of time domain analysis and provides a clear, more practical approach for system design. Thank you.